I'm going to explain to you today a little bit about limiting reagents and exceeding reagents in stoichiometry using chemistry. Alright, so first of all, what is a limiting reagent and what is a exceeding reagent? Well, you want to think about it as an analogy. First of all, if you pour 40 liters of gas into your car, you'll probably get 100 miles out of it. But if you pour 4 liters of gasoline into your car, there's no way you're going to get 100 miles on it. So that's how limiting reagents work. If you don't have enough of the reactants in a reaction, you don't get enough of the product. So let's start off with an example. We have, start right here. Say we have ferric oxide plus aluminum, and it produces iron and aluminum oxide. Alright, so let's balance the equation first, of course. We have 2 aluminums, and we have 2 irons, and that's about it. Alright, so we want to know how much aluminum oxide is produced, knowing that we have, and these are givens, 50 grams of ferric oxide and 50 grams of aluminum. So knowing that we have 50 grams of each, how much aluminum oxide is produced? Well, first of all, we got to look at stoichiometry as ratios. The easiest way to do this is looking at the coefficients. First of all, you have 1 mole of iron 3 oxide. You have 2 moles of aluminum, 2 moles of iron, and 1 mole of aluminum oxide. What that means is to produce 2 moles of iron and 1 mole of aluminum oxide, you're going to need 1 mole of iron oxide and 2 moles of aluminum. But it doesn't mean that it has to be 1 mole, 2 moles, 2 moles, 1 mole. It means that the ratio has to be that. So this could be 2, 4, 4, 2. So first of all, let's know how much moles we have of each. So in order to know how much moles we have, you have to divide, of course, the amount of grams. Let me erase this. You have to know the amount of grams we got. We have 50 grams. And we have to divide it. I'm using this one right now, ferric oxide. We have to divide it by the molar mass. And I'm just going to round it off right now. Molar mass is about 159.7 grams over mole. Now, you don't round ever use stoichiometry. You only round at the end. But for purposes of the video, I'm going to round it off so I don't have to write a bunch of numbers. This will give you about 0.313 moles. Now, how much do we have of aluminum? Aluminum we got, you know what, let me just write this one as a reminder. Fe2O3 equals 0.313 moles. Alright. How much aluminum we got? The same process, we got 50 over its molar mass, which is going to be 26.98 approximately. I'm not going to write the whole numbers. Which equals about 0.927 moles. Alright, so right now we know that our reactants have one of them has 0.313 moles and the other has 0.927 moles. So how, with this information, are we going to know how much it produces, how much aluminum oxide is produced? Well, we already said that the ratio is 1 to 2 is going to equal 2 to 1, right? 1 being ferric oxide, 2 being aluminum, 2 equals iron, and 1 equaling aluminum oxide. So we only have to put in the number 1, the lowest of the coefficients in the reactants. So the lowest of the coefficients is going to be 1. And the 1 belongs to ferric oxide. So let's just substitute 1 for ferric oxide's molar mass. Molar mass, not even moles. So instead of writing 1, we write 0.313. Let's say this is our 1. So it means that the ratio aluminum has to be twice as much. So what's 2 times 313? Okay, it's a 0.626. Right, so now we say that aluminum, if we have 3.313 moles of ferric oxide, we need at least 0.626 moles of aluminum to produce what's going to be produced. And we continue. We just pass on this. The iron's going to be also 0.626 because it's the same ratio, and aluminum oxide is going to have exactly 0.313 moles. Now, voila, we already know how many moles of aluminum oxide we have. So with that, we can already calculate how much grams it's going to produce. So let's say aluminum, again, let me just take this off. I'll leave the moles as a reminder. Alright, so we have that aluminum oxide equals about X, because we don't know how many grams it produces, over its molar mass, which is about 101.96, rounded off. And this is going to equal this amount of moles, 0.313. So to get the X, of course, we multiply these two together, because it would look like this. So the X goes here, this multiplies with this, so X equals about, so here 31.9 grams, let's just say that. So 50 grams of ferric oxide is going to produce exactly 31.9 grams of aluminum oxide. So how do we know that this equals, how much the limiting reactant is going to be? Like, how do I know that ferric oxide was a limiting reactant and not aluminum oxide? Well, we can go back to the ratios. And we have to start this process all over again, basically. So the ratio was 1, 2 equals 2, 1. Alright, aluminum, how much is aluminum? Aluminum was 0.9, right? 0.9 grams. We had said that before. If you don't remember the video, I'm sorry, you can put it back. So let's just say that here is going to be 0.927 moles. I'm sorry, moles. Because this is aluminum. So right now, before we took ferric oxide and we put in all the factors because we multiplied it by 0.313 moles, which was ferric oxide. Now, we're doing it again, but using aluminum as a reference. So if aluminum is supposed to be twice as much as ferric oxide, then half of this is going to equal the moles of ferric oxide, which means it would be about, I don't know, 0.45 moles, whatever. And then here is going to also equal 0.927. And aluminum oxide is going to equal how much moles ferric oxide has, because it's the one with less coefficients. So it's going to equal 0.45 approximately. So now we can just start this process again, but instead of finding how many grams of aluminum oxide we have from 0.313 moles, we do it by 0.45 moles. So again, same process. Aluminum oxide equals X over 101.96, which is going to equal instead of 0.313 is going to equal 0.45 moles. Multiply this. X is going to equal roughly about 94.5 grams. Now look at the difference. Before we had, how much was it? 31.9? 31.9. With ferric oxide as our limiting agent, aluminum oxide produced 31.9 grams. But assuming that aluminum could have been our limiting agent instead, we got 94.5 grams. This is what, like a 68.5 gram gap, right? So what this means is, had we had enough ferric oxide to reaction with aluminum, had we have enough to produce for aluminum oxide to have been used entirely, so that aluminum wouldn't have been the exceeding reagent. If aluminum was entirely used, then 94.5 grams of aluminum oxide would have been produced. Since only 50 grams of ferric oxide were used, which were about 0.313 moles, it wasn't enough for all of aluminum to be consumed. So only 31.9 grams were produced. So had we had enough, 68.5 grams more of aluminum oxide would have been used. So, and the same process can be done to know how much iron we got. Or we can even do it to know how much specifically aluminum from aluminum oxide we have. So this same process of comparing the ratios of moles to each other and substituting it to know what values is the least and which are the most can be used entirely. So this is basically the trick to stoichiometry and limiting reagents in a nutshell. So thank you for listening and thank you for watching.